Now, in the last couple of lectures, we talked about doing a test on a proportion when we have two samples. Now, in this lecture, we're going to do the same thing, but with sample and proportion and sample and population means. So the procedure, just like the procedure for two proportions, is going to follow the exact same process as for all the other tests that we've done, only with a different formula for the sample statistic. Now, I've got all the key elements of our test here, and I know it looks like a lot, but they're the same elements of every other test we've done. Right? First, we've got our definitions. Right? There's the population means, the sample sizes, and the sample standard deviations. Now, the requirements are also similar to what we've seen before. Right? We're assuming that we don't know the standard deviations, the population standard deviations, and we aren't going to make any assumptions about their values. Specifically, we aren't going to assume that they're the same. Now, the samples have to both be simple random samples, and they have to be independent. And finally, at least one of these two requirements has to be true. Either both sample sizes are large, specifically we're talking greater than 30, or the population from which both samples are drawn have to be normally distributed. Now, if those requirements are met, then our test statistic is given by this formula. Now, I'm not going to go through the derivation, right? The process is very similar to what we did for the test statistic for when we're talking about two proportions. It would be great practice for you to go over that procedure, then see if you can modify it to get this formula, right? And finally, the degrees of freedom down here at the bottom will be the minimum of the degrees of freedom of the two individual samples. So I've got an example here for us to look at. And you see this is really kind of playing off of the same scenario that we looked at in the last lecture when we were talking about proportions. We have a teacher and she's got a new method for teaching. In the previous example, we looked at the proportion of students who met the benchmark. Now, we're looking at their average grades, right? So we know that the current class has an average score of 82, so that's X bar 1 will be 82, and a standard deviation of 2.3, so S2 is 2.3, and the sample size, that's the class, let's say the current class has 22 students. And then we've got the information for the previous class, so X2 bar, let's see, in the previous year the average was 79. The standard deviation was 2.1, and her previous class size was 23. Okay, so those are kind of all of our numbers. Right now, let's see what is our claim. Right, our claim. It's in the last sentence here. The new method is better. New method is better. Our null hypothesis, remember, it is always, whoops, not the proportions anymore. It's always that the population means in this case are the same. And my alternative hypothesis, that's going to be that the new method is better, right? So mu1 is greater than mu2. Now, thinking about requirements, right? The requirements, we don't know the standard deviation, the population standard deviation, so that's okay. Both samples are independent. Yeah, there's no reason to believe that one class is going to somehow affect the other. And as I said in a previous lecture when we talked about this, you would have to be a little concerned. You have a student repeating the grade. If so, now that wouldn't be independent because they have kind of prior knowledge, and you can fix that by just excluding that student score. And the two conditions, okay, our sample sizes aren't large. They're not greater than 30. However, we're talking about test scores, assessment scores. So it's probably a reasonable assumption that the scores of the entire population will be normally distributed. So I would say we have a pass on requirement 3B, and that's good enough. We only needed one of the two. Okay, so now we can do our calculations, right? The t, and remember this, we're talking about means here, so I use the letter t on purpose. This is a t-score that we're calculating. It's x1 bar minus x2 bar divided by the square root s1 squared over n1 plus s2 squared divided by n2, and again square root of that whole thing. All right, now we're just going to put the numbers in, right? We're just going to be super careful. 82 minus 79 divided by, let's see, I mislabeled this here, didn't I? That should be a 1. So it's 2.3 squared divided by 22 plus 2.1 squared divided by 23, square root of that whole thing. Now you go to your calculator, right? My calculator tells me this comes out to 4.5633. Okay, so now where are we going to go next? What are our degrees of freedom? Well, it's the minimum of 21 and 22. So we're going to use 21 to calculate our p-value. Right now we're doing a one-tailed test, and it's to the right. So I'm going to want the probability that t is greater than 4.5633. That's my test statistic, right? And this is a really small number, 0.0001, right? That's where we end up. So if you compare this to alpha, right? Our alpha value is just 0.05. This is less than alpha, which means the likelihood that the result that we're seeing here is occurring by chance is really, really small. So there is sufficient evidence to reject the null hypothesis, right? Which means, and again, you know how I do these. I just because it makes it clearer in my head what we're doing, I kind of lapse into plain English for a minute. We don't like the null hypothesis, which means we do like the claim, right? So I would say that there is sufficient evidence to support the claim that the new method is getting better results than the previous method. Okay, so that covers means, and we talked about proportions in the last couple of lectures. So where are we going to go next? Well, one of the assumptions that we've been making throughout these discussions here so far is that the two samples are independent. Well, what if they aren't? Right? What if they aren't? Well, that's what we're going to talk about in the next lecture. What if the samples are somehow paired? For example, what if the data is coming from husbands and wives? Right? In that case, the data kind of pairs up in a natural way. The husband's value pairs with the wife's value, and also there can be questions about independence. Right? It's more reasonable to think that a husband and wife are going to feel the same way about an issue. It's not guaranteed, obviously, but you got to figure it's more likely that they will feel the same way than it would if you were just talking about two completely random people. So this kind of matched pairs analysis is where we're going to be going in the next lecture.